General Organic Chemistry. Today's topic is hybridization, in which we study the introduction of hybridization and how we can find hybridization, bond lengths, bond strength according to the hybridization, reactivity, effect of hybridization, and acidity and basicity of various organic compounds according to the hybridization. Hybridization. Different orbitals mix together to form same orbitals. How different? What is the difference between such orbitals? Remember, they have different shape, different size, and different energy. When they combine together, they form orbitals with same shape, same size, and same energy. This mixing is known as hybridization. Now, the types of hybridization are many, in which s orbitals, p orbitals, and d orbitals can mix together. But in organic compounds, as carbon is the basic constituent of organic compounds, so carbon undergoes s and p mode of hybridization. It means that in carbon, only s orbitals and p orbitals can mix together to form same orbital known as hybrid orbitals. Atomic number of carbon is 6. Its electronic configuration is 1s2, 2s2, and 2p2. This is its valence shell. 2s and 2p subshell are present in this valence shell. Here in 2s we are getting 2 electrons, while in 2p there are 3 orbitals containing 2 electrons. This is 2px, 2py, and 2pz, while this is 2s orbital. This is the ground state electronic configuration of carbon. Before hybridization, it goes to excited state. In excited state, one electron from s jumps into the empty p orbital. This electron jumps over here, and we get the electronic configuration now: 2s1, 2px1, 2py1, and 2pz1. If we draw these orbitals on energy diagram, you can see that 1s, it has 2 electrons and they are at low energy, while 2s has 1 electron and it has high energy than 1s, and 2p is the highest energy subshell and it has now 3 electrons in each of its orbitals. Now the mixing started. The mixing starts. Now look at the second diagram. In this diagram, you can see that 1s has its own energy level as it was before, but the 1s orbital of 2s and 2p, they all mix together and forming new set of orbital at energy a little high from s and little below from y, p orbitals. Means now these 4 orbitals have same energy and they will have same shape and same size. And if we represent these on carbon atom, for example, this is carbon atom nucleus. Now these orbital will be shown like this. This is one sp3 orbital, second sp3 orbital, third sp3 orbital, and fourth sp3 orbital. All these are sp3 orbitals. In this shape they formed, or the geometry they formed, is known as tetrahedral. Tetrahedral. All have same size, same energy, same shape, and the angle which exists between them or among them is 109.5 or 0.28 something. This is the angle which is known as tetrahedral angle. This type of hybridization is sp3 hybridization, in which one s orbital and 3p orbital mix together. Now the second type is sp2. In sp2 hybridization, one s orbital and 2p orbital, they will mix together and will give 3 hybrid orbitals, and one p orbital will remain unhybrid. It has its own energy, shape, and size, while the 3 hybrid orbitals have their own same energy, same size, same shape, and all are known as sp2 hybrid orbitals. Now on carbon nucleus, these orbital will occupy the places. This is one sp2 orbital, second sp2 orbital, and third sp2 orbital. All these are sp2 orbital. They will be at equal distance from one another, giving rise to an angle of 120, and the geometry they gain is known as trigonal planar. That is trigonal planar. Now what happened to this p orbital? This unhybrid p orbital will remain with its own size and shape and energy and will be looking like this. This is that unhybrid p orbital. It will lie at an angle of 90 to the 3 hybrid orbitals. So this was sp2 type of hybridization. The next is sp type of hybridization. In sp hybridization, one orbital of s and one orbital of p, they will mix together, giving rise to two hybrid orbitals sp and sp, while the two unhybrid orbital remains on their own properties. This is the sp mode of hybridization. Now making them on the carbon nucleus, this is carbon nucleus. These two hybrid orbital will lie at 180 degree from one another. This is sp and this is sp, and the angle that will be 180 degree between them, and this type of geometry is known as linear geometry. Now the remaining py, pz, you can take px in a hybridization, you can take py in hybridization, no problem. In this case we took that px and s orbital hybridized together, py and pz are unhybrid. These unhybrid orbital will be shown like this. This is py with its dumbbell shape and its energy. This is py, and this is pz with its dumbbell shape and shape, size, everything is different. So the blue one, two, these are sp hybrid orbital, while this dumbbell shape on y-axis is py orbital unhybrid, and this is pz orbital unhybrid. So this was the introduction of hybridization, that how many types of hybridization can take place in carbon. There is sp mode of hybridization, no d orbital is involved, only s and p orbital participate in the hybridization, and there are three types that we have discussed: sp3 hybridization, sp2 hybridization, and sp hybridization. The next is that how we can find that a carbon is which type of hybridized, sp3, either sp2 or sp. Finding hybridization of carbon. How we will find this one? Very easy. Let me draw three carbons. This is carbon, carbon, and carbon. When you see that all the bonds formed by the carbon are single covalent bonds or sigma bonds, then carbon will be sp3 hybrid. Remember, carbon is tetravalent. It can form 4 bonds only. The next one, if we see that carbon has formed a double bond and 2 single bonds, then the carbon will be termed as sp2 hybrid. Remember this point. When you find that carbon has formed a triple bond and a single bond, or carbon has formed 2 double bonds, then in both of these conditions, carbon will be sp hybrid. This single bonds of carbon, you will find them in alkanes. In alkanes, all the carbons are sp3 hybrid. This double bond of carbon, you will find it in alkenes. When you get one double bond, they are alkenes. Triple bonded carbon is found in alkynes. In this type, it's also an alkene, but the same carbon has formed 2 double bonds. So it's also a member of alkenes. So this is a simple trick that how you can find hybridization of carbon. Let's try some example. Look at this first. You can see that all the bonds formed by the carbon are single covalent bond. So all carbon in this example are sp3 hybrid. Each carbon is sp3 hybrid. This is the clue for this methyl group. You can see this is carbon single bond to the left side carbon, single bond to hydrogen, single bond to hydrogen, and single bond to hydrogen. Now, if you look this CH2, this carbon is bonded to other carbons with single covalent bonds on its either sides, and the remaining 2 bonds are formed with hydrogens, 2 hydrogens becoming CH2. In this example, this carbon is sp3 hybrid. Now, this carbon has formed a double bond, a single bond with hydrogen, and single bond to the left side carbon. So it is sp2 hybrid. This carbon is sp2 hybrid. Now look at this carbon forming 2 single bonds and 1 double bond with oxygen. This is sp2 hybrid. And the last one, CH3, it is always sp3. The next one, CH3, sp3 hybrid. CH2, it is sp3 hybrid. Now this carbon forming a triple bond to its right side with the next carbon and a single bond, so it is sp hybrid. Looking at the last carbon, you can see that this carbon has formed a triple bond towards its left and a single bond with this hydrogen, so it is sp2 also. This is sp3, sp2, sorry, sp3. This is again sp with nitrogen. In this example, sp3. Now this carbon is sp, it is sp2, and this is sp3. So this is a trick how to find the hybridization of carbon. Another thing you must have to remember, sp3 carbon forms all sigma bonds. These are 4 sigma bonds. sp2 carbon form 3 sigma bonds and 1 pi bond. sp carbon forms 1 sigma bond and 2 sigma bonds, while 2 pi bonds. In a triple bond, there are 2 pi bond, 1 sigma bond. In a double bond, there is 1 pi bond and 1 sigma bond. While in this case, there are 2 pi bonds and 2 sigma bonds. S characteristics and P characteristics percentage: sp3 orbital, sp2 orbital, and sp orbital. In sp3, S character is 25% and P character is 75% because the ratio of S is 1:3. In sp2, this is S ratio, this is P ratio. In sp2, S is 33.3% and P character is 67.3%. Here, S ratio P, this is 1:2. This is the ratio. In SP, we can find that S 50%, P is 50% because they are mixing in 1:1 ratio. This percentage will help us in finding the lengths of the bond, the strengths of the bond, as well as the acidity and other types of reactivities. Size of the hybrid orbital. Remember, S size of a hybrid orbital that depends upon the percent S character, and it is inversely proportional to the size of the hybrid orbital. We can say that sp3 hybrid orbital has greater size than sp2 and sp2 has greater size than sp, because if you look at the S character, it has 25% S character in sp3. In sp2, the hybrid orbital has 33.3% S character, while in sp, S has 50% S character. If you look at the diagram, this is carbon's nucleus, and this will be sp hybrid orbital. For sp2, this is carbon nucleus, and this will be sp2 hybrid orbital. For sp, this is carbon nucleus, and this will be the sp2 hybrid orbital size. Electronegativity of hybrid carbon atom. Remember, electronegativity percent S character is directly proportional to the electronegativity of carbon atom. So we can say that in sp hybrid carbon is more electronegative than sp2 hybrid carbon, which is more electronegative than sp3 hybrid carbon, because in sp hybrid carbon there is 50% S character. In sp2 there is 33.3% S character, and in sp3 there is 25% S character. This S character help us to understand the acidic nature of that carbon. Bond length variation. This is an alkane in which carbon is bonded to another carbon with a single bond, and the carbon is again bonded to hydrogen with a single bond. Here, the length of this bond between carbon-carbon is 1.54 angstrom, while that of carbon single bond hydrogen is 1.112 angstrom. This is carbon bonded to another carbon with a double bond and then bonded to a hydrogen with a single bond. Here, the bond length between carbon-carbon is 1.34 angstrom, while the bond length of carbon and hydrogen is 1.103 angstrom. This is another in which carbon is triply bonded to another carbon atom, this length becomes 1.20 angstrom, and carbon single bond hydrogen length decreased to 1.08. If you look, this is happening due to hybridization, in which every length, carbon hydrogen length, compare these, carbon hydrogen length and carbon hydrogen bond length. Similarly, you can compare carbon carbon bond length and carbon carbon bond length. This is happening because of the S character, percent S character. If this S character percentage is high, the bond will be shorter. So it is inversely proportional to bond length. Here, carbon is sp3 hybrid. In this example, the carbon is sp2 hybrid, while here carbon is sp hybrid. And the percent S character, we have 50% in sp hybrid orbital, 33.3% in sp2 hybrid orbital, and 25% in sp3 hybrid orbital. This S percentage affect both the lengths of the carbon bonded to hydrogen and carbon bonded to another carbon. In all cases, bond strength is measured by the energy it needs when it is broken down, or the energy it releases when it is formed. Here, carbon bonded to hydrogen, all are single bonds, but the energy is different. In this example, carbon is sp3 hybrid and hydrogen is S. This sigma bond is formed by the overlap of sp3 hybrid orbital and S, having the energy of 104 kilocalorie per mole. The next example, this carbon is sp2 hybrid, like in alkene, and hydrogen has S orbital. This is sp2s overlap in alkene, and the bond energy is 106 kilocalorie per mole. In the third example, we are getting 121 kilocalorie per mole. This is alkyne carbon, sp hybrid, and S for hydrogen. So it is sp-s overlap. Now coming towards the carbon-carbon bond, carbon-carbon single bond is formed by the sp3-sp3 overlap. Carbon-carbon double bond is formed by sp2-sp2 overlap, and carbon-carbon triple bond is formed by sp-sp overlap. And here we can see that the energy increases as we are going from a single bond to a double bond, then to a triple bond. These are the values. This data shows that percent S character is directly proportional to the bond strength. When the S character is high, the bond will be stronger. So we can write that sp3 bond, sp3-sp3 overlap bond is weak than sp2-sp2 overlap bond. It is weak than sp overlap bond. So S character directly related to bond strength in organic compounds for carbon. Acidity of hybrid carbon atoms. Remember, the acidity of an atom depends upon the electronegativity of the atom to which the hydrogen is bonded. For example, if we take the example of water, in which hydrogen is bonded to oxygen, NH3, in which hydrogen is bonded to nitrogen, and acetylene, in which hydrogen is bonded to a triple bond carbon. Here, water is more acidic than ammonia, and ammonia is more acidic than acetylene. The reason is that oxygen atom is more electronegative than nitrogen, and nitrogen in turn is more electronegative than carbon. So we can write that acidity is directly proportional to the electronegativity of the atom to which hydrogen is bonded. Now coming towards the hydrocarbon. In hydrocarbon, an alkane hydrogen is less acidic than alkene's hydrogen, which is less acidic than alkyne hydrogen. Means that if a hydrogen is bonded to a carbon that is sp3 hybrid, this hydrogen is less acidic than a hydrogen bonded to sp2 carbon. This sp2 carbon is more acidic, and this is less acidic than alkyne's carbon, in which carbon is triple bonded and single bonded to a hydrogen. This is because here carbon is sp3 hybrid, in alkene carbon is sp2 hybrid, and in alkyne carbon is sp hybrid. sp3 hybrid carbon has less electronegativity than sp2 hybrid carbon, and in turn sp2 hybrid carbon has less electronegativity than sp hybrid carbon. Though the same carbon atom is here, but its electronegativity varies because of the hybridization types. pKa values are easily indicated for more acidic or less acidic. If we take acetylene, carbon status CH, triple bond CH, then it is ethine. Another one is ethene, CH2 double bond CH2, and ethane, CH3 single bond CH3. Their pKa values for acetylene or ethine, it is 25. For ethene, it is 44. And for ethane, it is 50. Now remember that pKa is inversely proportional to acidity. If pKa value is high, the acid will be weak. So from left to right, the pKa value increases and acidity decreases.